Hi, everyone, and welcome back to another episode of Math Talk. It's been a little while. As just a quick update to my audience, I've been preparing for my candidacy, so that's why there's been no videos, not even book reviews. And there probably won't be any more videos until the winter break is when I'm sure I'll be making things more regularly. But I was able to find some time to have a discussion today with my friend David, who's a PhD student at York University. So, hi, welcome to the channel.
Hey, Christoph, thank you for having me.
And so we actually met each other. My supervisor gave an online course in winter 22, was it? Uh,
Yeah,
and on, stuff related to the Langland's program and a particular view in a particular corner of the Langland's program. And so we originally met through that class. But do you want to give the audience just a brief idea of what it is you're working on at the moment?
yeah, sure. I mean, uh, broadly speaking, I work on arithmetic dynamics and more specifically in something called the variation of the canonical height among families of morphisms of varieties.
Excellent. And so now that we know that we're what you're doing now, I normally like to start off the interviews by going all the way back to the beginning and ask, how did you first get interested in mathematics? If you can even pinpoint a sort of area or time, like were you someone who was clearly interested as a kid, or did it take you until you got to university? And sort of what was was there someone or a book or something that really sort of sparked that initial interest?
Yeah. So yeah, I think I remember very well the moment that I fell in love with math. I must have been 13 or 14. Um, so the math one learns in high school is usually not the prettiest or the most astonishing mathematics. And I come from a city. I'm from Colombia, and I come from a city called Cali, which uh, I don't think mathematics is one of our major products.
Hmm.
But I did good in my classes, and I met this teacher. I was in the eighth grade, and she pushed mathematical Olympiads, not only in my city, but in the whole nation. And when I was in the ninth grade, I attended uh, to a school. When you did good in the first rounds of the Colombian Olympiads, you were invited to a last round in the capital city.
Hmm.
Um, and I mean, it was the first approach I did to pure math or to something different than high school. It's focused on elementary number theory, what they call algebra, which is at the time was just inequalities, then Euclidean geometry and some combinatorics. And I was young; I didn't have the skills to take the best out of the school, but I got a book. And when I came back home, I started going through the book, and I got to induction. Um, and I remember very well me sitting down in the desk in my room in my my parents' house, and I started playing with numbers. And I noticed. I mean, this is very elementary, but it's how I got into math. And so, if you start adding one with three, you get four, and then one, three, and five, you get nine. And in general, if you add one, three, five, all the way to 2K, plus minus 1, so you add the first k odd integers, you will always get k squared. And I did the induction. I mean, I did it on my own. Like I added a lot of odd integers, and noticed that was the pattern, and just try to prove it, and it was true. And that, I don't know, that feeling of showing that something is true just made me fall for it. And
right.
at that time, I decided that I was going to do mathematics, and then I went to the university to pure math. And it's funny that in the undergrad, I was kind of sick of mathematics. So when I finished, I didn't want to do more math. And I went to the industry to work. I worked for the National Intelligence Department in the Army. I worked for something like Uber Eats in doing data analysis. And then I noticed that there was an opportunity to create a business doing machine learning and all these hot topics now in data science, software development. And my business partner and I created this business. For 2-3 years, we developed projects for insurance companies, for marketing companies, for transportation companies. It was very cool. When you start a business and you're the boss, you need to learn a lot of things that you didn't even know you didn't know.
Right.
But then at some point, one of my mentors back home invited me to this seminar on elliptic curves. And I was hooked back again. That's how they got me again. And I
that's
started
what
my
reignited the
master's.
passion.
Yeah, and then I started my master's, did my master's, and yeah, I'm in my 3rd year now at York, and still working in number theory. That passion for number theory never stopped. And yeah, that's the short story of my life.
So I actually had a couple questions going back a bit. So I wonder if do you think that initial sort of discovery you made about adding odd integers and using induction, do you think that sort of had a lasting impact that informed your decision to number theory? Like when you first did your undergrad, were you mainly interested in number theory, or is that just something you ended up coming back to once you saw this talk on elliptic curves?
Yeah, that was something I came back later. So I think even though I went to the Olympiads and I started thinking about math early on in life, didn't really have the formation to like how to study, how to the studying habits. And in my undergrad, I really couldn't see much beyond what was presented in the classes. I could follow and then present exams, but this intuition and this deeper knowledge that you get, I only developed it during my master's. And actually, in my undergrad, I worked on logic. My thesis was on. So if you take a matrix and you see the columns of the matrix, those are some vectors in some Rn or Cn, whatever you're studying, and you can so I worked on matrix, which is like a generalization of this linear dependence of vectors. So let's say you have 3 vectors that are linearly dependent, and the matrix is the vectors have length m, and you have n columns in your matrix. Then the matrix will be a pair. The first one will be 1 to n because you have n columns, and then The second one will be a subset of the power set of n, which labels the independent columns. So if the first, fourth, and fifth column are linearly independent, then in your matrix you have the set, and then a subset of it that is 1, 4, and 5. So what I said. And that also generalizes algebraic independence in combinatorics. Like it also generalizes the having cycles in graphs. So it generalizes like 9 notions of independence. And my goal was to characterize infinite matrix, because the issue with, so if you have a set of n elements and you add one element or subtract one element, then the sizes are no longer the same. But if you have an infinite set and you add one element or take one element out, the sizes are the same. And that issue made it difficult to characterize matrix. And during the year I was doing my thesis, actually some guys came out with the actual axiom, because in logic you have all these first order formulas, and so they wrote the axiom, and essentially my thesis was worthless, but I learned logic and combinatorics. Yeah.
Interesting. Yeah, I do remember. I actually, so in my undergrad, it wasn't a full thesis. It was just for a course. I did a small paper on matroids associated to a graph. And yeah, I remember, now that you mention it, I remember there's a general process where basically you take some element and what is it? You remove the element, and then I think there's like the matroid you get from removing the element, and then there's some sort of quotient matroid as well, and you decompose it into those two things. Am I remembering that correctly?
That's one process, yeah. But like it depends on how you define your matrix, because if you make it out of a graph, then you define it in terms of circuits. So instead of having subsets of independent sets, you have subsets of circuits. And the thing with graphs is that if you have a circuit and remove one edge, then it's no longer a circuit. So if you define your matrix in terms of circuits, then that's the action you have to put. But if you put it in terms of independence, like if you have 3 vectors in R4, you can find another vector that is linearly independent to these 3 vectors. And so that's the action you put. That if you have a strictly less, a set that is of size strictly less than another one, you can find an element in a bigger set that you can put in the smaller set, and it's still independent. And I think that's called augmentation. I'm not an expert in either combinatorics or logic, and logic and I never returned to a friendship after writing my thesis.
So yeah, when you mentioned, the other thing I wanted to ask you as well is, you mentioned that you were sort of sick of mathematics at the end of your undergrad. Do you think that doing the competitions had an impact on that, or was it just that you ended up picking logic and not being as interested in it, or what do you think caused you to sort of grow tired of it at that point?
I mean, the main reason, and that's I think a rule in general in life, it comes from inside. Sometimes the outside world can be messy or great, but it all depends on how you are in yourself. And I wasn't ready to, I don't know, even to be a responsible guy, a person, an adult. So the pressure of university, and then becoming an adult and having to go out to the real world, and everything just became a lot to me. And you start, sometimes mathematicians or scientists can be a little, I don't know what other word to use, but maybe a little cocky. And it's so much competition and showing off, and that it becomes a burden. but right now I don't think. Well, people measure, but the outer world will be what it is. But right now I have more personal skills to handle the pressure, to handle I don't the stress of PhD, the living abroad,
Mm,
which is a good thing that, about when I got tired of it and then went to the real world, develop other skills. But even though I'm older right now than most of the people doing a PhD, I also have more experience in life, so I think that
mm,
plays a crucial balance so that yeah, so things work out better now than they did before.
right, right. Yeah, makes sense. And so then, so you went to a talk on elliptic curves, and that sort of, revitalized your interest. And then did you end up working on elliptic curves in your master's?
Yeah. Actually, kind of applied math. It's coding theory.
Mm,
Um, so and actually, protocols like Bitcoin or other digital asset networks nowadays use this encryption using elliptic curve. So
mm,
you have your elliptic curve over a finite field, and um, take a divisor of your Picard group, and you take a function on your that Riemann rock space that are like all the functions whose divisor plus the divisor you took are effective. So you take one of those functions and you evaluate it at finally many points of your elliptic curve, and that's your encryption.
mm,
Those values of that function, and and that's essentially empty hard to decrypt unless you have the key. And
right.
so my thesis was on counting information sets of such a code, and an information set in the simplest way I can think of is let's say our language is either yes or no. If you hear the letter Y, E, or S, you know that I said yes. And
Mm,
similarly,
mm-hmm,
if you hear N, O, you know that I said no. And so that um, in the information set language means that every information set or sets of size one are information sets for your code.
mm,
Because well, sometimes I mean, in the phone or through in the theory you call it a noisy channel. That's how information or messages get passed through. So counting how many you need in order to recover the message is sort of important.
I really like that example, actually. I haven't heard it explained like that before with the yes or no, and if you detect the one letter, that's a good way to explain it.
Yeah.
So you did this research in your master's, and then how did you end up where you are now for your PhD?
Yeah. There's this entrepreneur in Colombia. She created all these high-tech gyms. And she has this saying that luck exists, but is delivered at 5 a.m., meaning like
Mm,
at the end, there's always this factor of luck, but you need to work so that that factor ends up happening. And so during my undergrad, I essentially learned nothing. Um, I don't really know how I managed to finish my undergrad, but and then during my master's, he was like catching up to all these holes that I had from undergrad,
mm,
and um, I attended seminars on geometry. Well, logic I tried, but it just brings. I guess it brings me back to my undergrad, which was not a good time in my life, and
right.
I just logic and I are no friends. And a number theory, combinatorics, and this professor she got her PhD at York, organized this event at another town in Colombia, and she was like, "Why don't you come? You're been attending to all these things." And I was like, "But I don't work in combinatorics." And but I attended to this event, and in some talk or mini course about the like sort of Riemann-Hertz formula, or the Riemann-Roch theorem for tropical curves. I asked this question that, I mean, now I don't think it was that deep, but at that point it was a little of a higher level that I was expected to know. And so this professor at York noticed me, and we talked, and I told him, yeah, my interest is in our theory. He got in touch with this professor at York, my advisor, Patrick Ingram, and we started talking, and I guess we hit it off, and I applied, and I got in, and I just started following his advices and working on what he suggested. And well, at this point, it's nice. I feel that I don't know what I'm doing is maybe my thesis won't change the field, but I understand why it's sort of important and why people care about it. And so yeah, I'm glad of what I'm working on, and he's been so patient and allow me to develop, like, to have, because I mean, my dream is to get tenure somewhere and get a position and do math for a living. And when you're in that level, nobody is on your back like telling you do this, do that. So
Right.
he's been
Right.
very good at allowing me to develop that sense of responsibility on how much do I need to work on my own, not telling me, oh, you need to work more, you need to work less, just guiding me and hearing me. And it's been an amazing experience.
And I want to take this opportunity to point out to my audience, they're probably sick of hearing me say this, but this is yet another perfect example of why you need to network, why you need to go to talks, go to as many talks, as conferences, as summer schools as you can, because as everyone just heard, this is how things happen, right? This is how you meet people who become your supervisor or become future collaborators or become someone that tells you when you're on the job market as a postdoc or even looking for tenure track. Someone says, oh, hey, I by the way, we have a position at our university, just thought we'd let you know, or something, right? So here's yet another perfect real world example of why you should always go to these things. And I know it can be hard, maybe some of us are introverted and we like maybe some mathematicians like the solitary thinking, but at the end of the day it's it is still a social process, and we're still humans. So yeah, yet another reminder: go to talks, ask questions.
Yeah.
Yeah.
Yeah, I mean, even, I don't know, let's bring, I don't know, Grothendieck and Serre. I don't think they would have done the work they did if this Bourbaki group in France never existed. I don't know, even guys like Andreveyo, his biggest contribution, and that's a huge, delicate topic about the Taniyama-Shimura-Veil conjecture, or the modularity theorem, whatever you call it, that would have not happened if they had not met each other. And those are the brightest among the brightest minds of our field. So if even them needed, well, yeah, they'll let the rest for sure do.
Yeah, of course. Yeah, there was actually a post on Reddit recently where I gave an answer. It's probably the most karma or points whatever I've gotten from a post in a long time. Someone was asking, they were saying something like, oh, these crazy proofs that you see, I have no idea how anyone could have come up with them. And, my answer was something along the lines of, well, of course there are people who are truly creative geniuses, and it's hard to match them. You shouldn't necessarily expect to, but even these so-called creative geniuses aren't proving these things in a vacuum, right? They aren't just sitting at their desk and magically this idea comes out of thin air, right? They're interacting with people, with their colleagues. There's ideas going back and forth, and especially something like, this person brought up the fundamental theorem of Galois theory as an example, and the modern version of that looks nothing like the original development, right? The modern version is nice and polished, and we've had, hundreds of years to develop the pedagogy and the theory around it. So it's this clean, beautiful thing you can do in a semester of an algebra course. But the development of the theory was this messy, long, slow process that involved a whole bunch of big and lesser known names in mathematics alike, right? That got it to where it is today. So yeah.
I like this. Territao has this blog um, in which he actually, because you touched on a I don't know theme of mathematics, and like there's these geniuses and others we will never be like them, but um, he has this, and it's a thread of entries in this blog in which he explains why is every mathematician equally, but not only equally valuable, but equally important. And the way I will put it, I come from a country that in which the only sport that matters is soccer. So I will bring Lionel Messi or Cristiano Ronaldo. Like, what would happen if they were the only two soccer players in the world? Like,
Right.
there would be no game.
Right.
So yeah, I mean they're the famous one, and maybe not anymore, but the best ones in their generation. But if their teammates did not exist, if all the leagues around the world did not exist, they would have not been what they were. So that's
Yeah.
nice to
Yeah.
remember that you don't need that to be the next Lionel Messi, or in our field, I don't know, the Cholce or Tao or any name. I don't know, like nowadays in Canada, Zimmerman. You don't need to get to put yourself that pressure. You just need to enjoy the ride. Whatever you get, if you enjoy the ride, you'll feel satisfied.
Yeah. Yeah. So speaking of enjoying the ride, why don't we delve a bit deeper into the ride you're currently on
Okay.
in your PhD? Do you want to tell us a little bit more in depth what it is you're working on, some of the big ideas?
I'll try to explain why my research could be or is important, and how dynamics can be used to study number theory for, I mean, those of the audience that don't have the background on arithmetic dynamics, just I guess to motivate the field. So let me just maybe call this motivation for arithmetic dynamics. So first example, if you have an elliptic curve, of course, I think Drew Sutherland at MIT said once, like, every talk in math should start by let E be an elliptic curve, and then just go from there. So E is an elliptic curve, and consider the map. So an elliptic curve is not only a geometric object, but it has a group structure on it. It's you can add elements and subtract elements. So suppose that you have the map that takes a point in your curve and sends it to the n times p. which is just adding the point with itself n times. So if P is, let's say, n torsion, meaning as a group, an elliptic curve has a mark point O, that is the identity under this addition law. So if P is n torsion, meaning that n times P gives you the identity element, then P is what we call, or let's say it this way, the orbit of P under multiplication by n is finite. Just let's write it like this for simplicity. And another way of saying this is that P is pre-periodic for the map multiplication by n. So, and since torsion points are dense in your elliptic curve, then in the dynamic world, we care about pre-periodic points. And those sets can be very different from one another. One example from Silverman is if you take the pre-periodic points of the map that sends every point to set every number set to the P, and you see these over the finite field of P elements, then by Fermat's little theorem, this is everything. But on the other hand, if you take the pre-periodic points for the map set to the P minus 1 for the same field, this is just now 0 and 1. So on the one side you have everything, and on the other one you have the least things you can have. So these sets of pre-periodic points can be very different in the same set. So the example I want to present on why is this important. So this was just an introduction. And now let's, this belongs to what now people talk about, the silver-pink conjecture, which is a generalization of Manny Mumford, Andre Oort, and all these results of unlikely intersections. So example I'll present is work by DeMarco and Mavraki. The example is taken from her paper in the Lawrence DeMarco's Arizona Winter School mini course. So let's suppose you have a.
So another, if I can jump in for a second. Another speaking of going to conferences, the Arizona Winter Schools are awesome. I'm not sure if registration for this one is still open. It normally closes, I think, end of November, beginning of December. So for anyone watching this who's a grad student looking for a cool number theory related winter school to go to, definitely check that one out.
Yeah, it's amazing. Like these years, the Clay lecture will be Barry Mazer. So it's
yeah.
It's incredible. So I'll use 3 ingredients. The first one is heights, which is just a way to measure arithmetic complexity. I'll use arithmetic equidistribution, which in the way I'll use it is due to Bilu, but many people have worked on that. And the third ingredient comes from complex geometry, or I will say potential theory / complex geometry. Which is just, I mean, I come from a number theory, so this is just a technical way to use arithmetic equidistribution. So the example is as follows. So it's, this is taken from Bogomolov, Hu, and Schinkel. I think this was the preprint is from 2017. And so the idea is, let's say you have an elliptic curve, I1. You have an elliptic curve to, let's say, all these are over the complex numbers. So E1 and E2 are given by equations on the complex numbers. And you have a projection given by relating a point P to its additive inverse. And similarly, you will have here a projection to the Riemann sphere or P1. And so the question is, when is, so let me define this set I as the intersection, let's say P1, and these are the torsion points of E1, inter the second projection of the torsion points of E2. So the question is, when is this set infinite? And the answer is, which they give the answer in their paper using Manning-Mumford or now Raynaud's theorem, is that I is infinite if and only if there is an isomorphism, not only an isogeny, but an isomorphism between I1 and E1 and E2, such that this diagram above commutes. And so, even though they do themselves in the paper to show that this is the case, there is a way to attack this using arithmetic dynamics. So, so let me just sketch a proof of this using arithmetic dynamics, which is on the work by DeMarco Nobraki, and again, it's presented in Laura DeMarco's course in the Arizona Winter School. But so let's say I is infinite, and let's just take a subsequence or a sequence of elements in I. So there are torsion points on the elliptic curves, and maybe a parenthesis here. You can, so I'll build two maps on the Riemann sphere. So let's say you multiply here by M. You have your projection one here. You have your projection one here. So you can build a map F1. Sorry, this is the Riemann sphere. You can build a map F1 from the Riemann sphere onto itself, such that this diagram commutes. And so being torsion in E1 means that the projection, so P torsion, is equivalent to P1 of P being pre-periodic for F1. And the same thing applies for E2. There's a map F2 such that, so let me just write this as this. P in EI is torsion, if the projection on the Riemann sphere satisfies that it's periodic for those maps. And so we can use I won't define the canonical height of associated to amorphism, but you can, just as height measures complexity, the arithmetic complexity of number, the canonical height associated to amorphism measures like the arithmetic complexity around the orbit. And so these two, the sequence that we built from the intersection of all the torsion points, the canonical height actually, so let me actually here use, measures when a point is periodic. So the canonical height of all those points is 0, and we can use Bilou's arithmetic equidistribution theorem. So let me just state Bilou as this. If Zn is a sequence of non-repeating algebraic numbers, let me define O of Zn as the orbit, the Galois orbit of Zn. Then these probability measures, un equal to 1 over the size of this Galois orbit for x in the Galois orbit. So then these are the Dirac. It takes value 1 at x and 0 everywhere. So this sequence of measures converges to the Haar measure on Sn. So this the Haar measure on S1. And another way of thinking about this statement is that if you have algebraic numbers, which okay, and you need one other assumption, that the height of your sequence converges to 0. If you have small points in complexity, algebraic points, algebraic numbers, then those numbers equidistribute with respect to the Haar measure, which is pretty surprising. And it's how one of the ways that dynamics shows that is intertwined with number theory, and I guess it's in the flavor of Langlands, like how everything is connected somehow. And so using that the height is 0, the canonical height with respect to F1, with respect to F2 of the sequence is small, then we can, this Bilou is over Q bar. So, and this is where at the end I'll show why my research is kind of useful. These elliptic curves were taken over the C, but our sequence or arithmetic equidistribution theorem is for, or at least Bilou's version is for algebraic numbers. So we're not quite there in the complex setting yet, but we'll get there. So essentially how we use this Bilou's theorem is to say that, and again, I didn't define the canonical height. I won't define these two measures that I'm talking, that right here. 1, 2. There are two canonical measures associated to the dynamical system given by the FIs that play this role, the role that this Haar measure plays in Bilou's theorem. So there are two natural measures, and the fact that these heights are 0, and the fact by Bilou's theorem, you have that so these measures will converge to this guy and to this guy. So using the technicality here is that if you have a covering map of P1 from an elliptic curve, it's determined by the two torsion points in the elliptic curve, because those are the branch points down in P1. So this, by some other arguments, show that E1 over C, the complex point of E1 is isomorphic to the complex points of E2. And again, this is when E1 and E2 are given by equations given by coefficients that are algebraic numbers. And so how do we go from that place to the so let me call this how to reduce the complex setting to the algebraic setting. This example is again taken from the Arizona Winter School on the course by Zimmerman. And so assume we have this elliptic curve given by y squared equals x cubed plus x plus t, plus pi. So this is not algebraic. We'll build the following. We'll build a new elliptic curve over this algebra given by y squared is equal to x cubed plus x plus t. So when you specialize t equals pi, e pi, let's call this guy e pi, let me call this guy e sub t, is an specialization. I don't think this is the right terminology, but you obtained e pi by plugging in t equals pi on your big elliptic curve. So geometrically, what is going on is that you changed this non-algebraic equation by the following. So let's say here you have pi, and here you have your elliptic curve e pi. And for all these points, you also have an elliptic curve, for which most of them are given by algebraic equation. They are algebraic. So by some limit process or approximation process, you conclude that, let's say, I don't know, minimum holds for all the points that are algebraic. Then by some limit process here, you conclude the result for all your elliptic curves. And so this is where my research comes in, because this elliptic curve will give you a family of elliptic curves over C. And so again, studying the canonical height, studying the variation of that canonical height, since that's the key, one of the key ingredients we are using this canonical height. It's important to know how it varies as you start varying your family. And along those lines, I think Favre and Gauthier obtained a nice result last year, and just last month, a group in China obtained another result that I think that's what I will finish with. And let me just make sure that I will state it correctly. So this is called the dynamical Andre-Fort Leesford curves. So let's say you have a family FT of endomorphisms, let's say non-exceptional, which means these maps up here that occur as so that have an endomorphism of an elliptic curve above are called lattice maps. And so you don't want those. Non-exceptional means that it's non-lattice and non-isotrivial, but I won't get into what is every each of those words. But and let's say that they have degree D, each one of those. And so, and let's say these guys are endomorphisms of B. And so what the theorem says is that the following two conditions are equivalent. There are infinitely many t's in their curve, such that ft such that the critical orbits of ft, meaning the orbits of the points at which ft is critical, and then in the family, I won't define what it means, but a family has most one independent critical orbit. Yeah, this just happened last month, and this is along the lines of my research. You have a family of morphisms, and you start studying their canonical height, their critical orbits. These properties will be post-critically finite, and the idea is that these post-critically finite morphisms in the moduli space play the role of elliptic curves that have complex multiplication. I guess in the world of Shimura varieties, I'm not sure about that. This parallel is what suggested by Silverman, I think, and it's another bridge of how number theory and dynamics are intertwined together.
Hmm.
Yeah, that's all I wanted to say about my research.
Oh, fantastic. Well, thanks for sharing that. So one thing I'm a little curious about is when you have these curves that are changing with the parameter t, like, I know, of just playing around with some elliptic curves when, I've in Sage, like, just played around with some elliptic curves and changing their coefficients just for like elliptic curves defined over the integers. And I know if you you change one coefficient, then all of a sudden your curve can have very different properties. But it seems in some sense, if you only move t a very tiny amount, is it you expect the curve to have very similar properties outside, maybe, like, I imagine there's some very special points, right? You change it a bit, you hit that point, and then something strange happens. But is it the case that for t sufficiently close in some sense, you expect the curves to share many similar properties, or is it just way too chaotic?
The answer is that I have no idea, but at some sense, this process of spreading your elliptic curve even though like I have no idea of how the geometry of these specializations work as you vary them. All it's doing, or the way I use it, or I think people use it, is that you want things defined over a number field, or essentially over Q bar, so that you can use Galois theory, number theory, and by considering algebras over Q bar, instead of you can forget about the transcendental part of your equation, and just focus on the algebraic part. And I want to say that there should be a relation. That's what I feel, but I have no idea.
Yeah, I could easily imagine it goes either way. Like the natural thing to suspect is, oh yeah, of course, if they're you know close together, you imagine they have similar properties. But then I can also very much believe that it's just absolute chaos.
Yeah, yeah, that's one of the beautiful things about math. Sometimes your intuition is far from the truth.
Definitely, definitely.
I would say that was another time I really fell in love with math when some point in my undergrad it was called structural mathematics, when you prove that the size of the rationals is the same as the size of the natural numbers.
Mm.
That's I was like, but this cannot be like. Uh, uh, but yeah, infinite is a very interesting creature. And, I guess math migrated from that's from set theory. It's not as huge of a topic nowadays as it was last century.
Mm.
But yeah, the infinite is definitely an interesting creature.
Yeah, I've thought before I would have to sit down and really do some planning, but I've thought before of making some videos on all the different kinds of infinity and all the terms and definitions we come up with to try and describe the different kinds of infinities that we've found.
Yeah, yeah, and it's I don't know if you've are aware of this theory written somewhere. Yeah, like the ultimate assembly theory by professor at MIT, Max Tegmark, I think.
Oh yeah.
And he essentially says like the universe we live in is a mathematical structure. So like I don't know like what could it be? Because I don't know. When one comes from this three-dimensional space, one starts to think that like I don't know, the complex numbers or real numbers are the more natural geometrical setting for our universe. But then you start studying Lagrange and uh, how the p-adic structure is hidden, and not also hidden but determines that a global structure, or the Archimedean structure, let's say. You start wondering, well, yeah, my mind tells me that the world is we live in the real world or in the complex world, but who knows? And well, these theories, I mean, I haven't studied physics at all, but what if it is? And what if we really need to understand infinity and come back to those questions from the last century? That yeah, because I think like once we hit the wall of the continuum hypothesis, like people were like, okay, we need to do something different.
Mm.
Um, and well, nowadays it's not a hot topic anymore, but I don't know. It's sort of fundamental at some level in order to build this universe of ours that is the mathematical world.
Mm. Well, I do know there are still set theorists
Oh
sort
yeah.
of have a belief that if we find the right large cardinal axioms, it will decide the continuum hypothesis.
Oh,
And I think there's sort of research and debate into that. I mean, of course, then we're just adding, that's us adding extra axioms already to ZFC. But so I'm probably butchering the argument. If there's any set theorists out there, they might be upset at the way I've explained it. But But I know that there is some sort of belief that there are certain large cardinal axioms that we should accept, and depending on what we take, that will settle the continuum hypothesis. But you bringing that up actually leads me into a question I normally like to ask at the end of these, and that is, how you feel about the whole math as a creation versus math as a discovery, Platonism, whole argument very naturally wrapped up in this, idea of Tegmark. So I guess generally speaking, where do you stand, if anywhere? Maybe you don't have a firm stance one way or the other.
Well, if I'm being completely honest, I have swing between positions as my career goes on. All I can say is that when you, like, I don't know, for instance, the Langlands correspondence, the fact that let's assume it was just an invention, the fact that all those things match together would make the reality that math is an invention really surprising. But then again, I don't think that the current way of understanding mathematics will allow us to. It would be essentially like bootstrapping ourselves, trying to lift ourselves from the boots. The way we try to do mathematics nowadays, and essentially how we hit the wall with the continuum hypothesis and Gödel's incompleteness theorem. I'll be very surprised if math is not real, and I like to believe that it is real, because I mean, otherwise, I think what I do for a living and what I want to do for a living wouldn't be as meaningful for me. It's beautiful. It's hard. You develop tools that may be used by the next Einstein in 200 years. But if it's just a game that I don't know, I would probably have an existential crisis. Yeah, that's my non-answer answer.
Well, I feel like every mathematician needs to have one or two existential crises at some point. Speaking of large cardinal axioms, I just had one back in September all about large cardinal axioms. So, yeah.
Yeah, set theory is nice. In my alma mater back in Colombia, logic is a big topic, and it's definitely very interesting. I don't know. There's these alternative axioms to, like, the axiom of choice. There's something called diamond axiom. Essentially, something called topological set theory, something like that. And yeah, it makes you get into all sorts of philosophical dilemmas. And but yeah, I agree with you. They're important because that's how you build resilience. This world is not easy. You pass 5 years, 10 years, a whole life without proving what you wanted. You still need to be okay, be happy, because that's how you essentially change the world. I think, like, if you can irradiate that desire, that passion for what you do, that professionalism, and that is essentially how I see the value of doing mathematics, and especially for someone coming from a developing country in which hard sciences, these, I don't know, elite or exquisite tastes are not as developed as they are in other places. And I think there's where the value is, in the community, in showing that you can, I don't know, live with passion, do love something, and that's how you actually, I feel you make an impact. Is not, I mean, if you see the news, if you see all the media, you get a little worried about the world. But I feel that there's a lot more people, I don't, coming out of sadness, depression, addiction, families reuniting, miracles essentially happening all over the world. But those don't make the news. Just they don't sell, I guess.
Mm.
And that's where I see the value of mathematics, regarding if it's a creation or a reality.
Mm. Well, I think those are some perfect words of wisdom to end off on, and to leave our audience thinking about for the rest of their day. So thank you so much for joining me. And
Yeah, no,
yeah,
thank you
this has
for
been
having
great.
me.